now. Alrighty, so let me just collapse that so I have some room to draw. So this short little tutorial is going to start with tonicity. And to do that, I'm actually going to take my computer apart so I can comfortably draw. And I'm going to draw some pictures. Okay, and like a good scientist, I need to label my drawing. All right, so let's talk about tonicity first. So I'm going to go ahead and define it, and then I'll draw what I mean by the definition, because as I'm sure you guys have noticed, reading the definition of a process in the book is all well and good, but just because you've memorized what the definition is doesn't mean that you've sort of internalized the concept, especially if they're kind of tricky or complicated. So let's first define. So tonicity describes a solution and it describes a solution specifically on the basis of that particular solution's ability to cause a cell to gain or lose water. So when I say a word like hypertonic, it's just one word, right? But there's a bunch of hidden meaning or assumptions in that word. So when scientists are using the words like hypertonic to communicate to you, if you're going into nursing, this matters a lot because you'll be administering IVs and you need to pay attention to whether the medication in the IV is suspended in an isotonic solution or a hypertonic solution or a hypotonic solution, because that's going to tell you the effect of the solution on your patient's cells. And if you get that wrong, that can have some very severe consequences for patient health. So I know that when you're learning this in 160, it doesn't necessarily seem like it's something that you're going to need to use again. But if you're on a healthcare track, you absolutely will. So it's good to start remembering it now and building up these concepts. So if I tell you that a solution is hypertonic, what I'm telling you is that something about the solution is going to cause water to leave the cell. Another way to say this is the solution has a lot of solutes compared with the cell. So I'm going to draw 3 beakers and I'll describe the beakers to you a little bit more once I've drawn them. So give me just 1 second here. So one of the nice things about Epic Pen is instead of drawing 3 crappy beakers freehand, I can use the shape function to draw 3 relatively good ones. Awesome. Okay, so now I'm going to put some solution in my beakers. I don't know if you guys can hear it, but my bulldog is right next to me and he is snoring. So if it sounds like there's a tiny gremlin on the microphone, it's just my dog. Okay, so I'm putting some solution in my beakers. I'm making it blue because that's the color that I happen to choose. And this is obviously looking pretty similar to your lab, right? So you had beakers and then you were putting little fake cells in the beakers, which were made out of dialysis tubing. So apropos of the lab stuff, let's talk about controlled variables. So controlled variables are going to be variables that I make sure are the same across all of the different treatments. So I'm going to say all of these beakers are, let's say, 100 milliliters of water. So they all have the same volume of water in them. That's important. And we're going to also assume that they're all the same temperature. But we're not going to assume that they're all the same tonicity. And so what I'm going to do, I'm not going to tell you what the tonicity of the solutions is yet. I'm just going to give them labels, and then I'm going to draw the behavior of a cell in the solution, and then I'll explain the tonicity feature. Okay, so this is beaker A. This is beaker B. And this one is C. And
yellow highlighter. Thank you.
alrighty, so now I have my cells, and I'm going to add some water direction to my drawing. So I want the skinnier arrow because I'm going to, oops. There. I want to be able to have room to write, so I'm going to make my arrows smaller. So the arrows here are going to be the direction of water movement. And of course, now my mom's calling me. So many interruptions. Okay, so you can see that the cell is behaving differently depending on which solution I put it in. And if I assume that the properties of the cell, so let's just assume that I have 3 exact duplicates of the same cell, and I'm putting them into beakers of unknown solution, and I'm watching the behavior of the cell to tell me something about the solution. So because I'm controlling the variable, it's, let's say, all cells same. It's another controlled variable. Okay. So another thing I'm going to state, because these are cells and they obey certain rules, is that if water is moving, it's moving because of osmosis, which is a passive transport, right? So it's just water moving along its concentration gradient without any extra energy expenditure. So I'm going to put passive down here. All right, so let's take this first one. So I have one arrow going in and one arrow going out, which means that it's not the case that the cell isn't having water enter or exit it, but rather it's going in and out at equal rates. Sorry, there was somebody that talked, but I couldn't hear what you said. If you want to repeat yourself, go ahead. Okay, so if I see that the cell doesn't change volume, so it's just a happy little circle, That means that the concentration of solutes, so in science notation, we use square brackets to represent concentration. So I'm going to say the concentration, of solutes. Dang it. There's only so many undo buttons I have. There we go. Solutes, that's what that means, is the same inside the cell as it is outside of the cell. Now, I'm not actually measuring the concentration of solutes inside of the cell, and I'm not actually measuring the concentration of solutes in the beaker. I'm basing my decision on my observation of the cell's behavior. So it could be 20% sucrose, it could be 15% saline, it could be a mixture. I have no idea. I don't know what the specific number is, but I know that my cell didn't change volume. It didn't gain weight or lose weight. It didn't gain water or lose water. So I can at the very least say that this solution is an isotonic one. Isotonic, meaning same solute concentration as cell. So that's isotonic. Another important piece of this is the vocabulary. Iso means same in Latin. So isotonic means same tonicity. Okay, so now we have a situation in which there's a lot of water leaving our cell.
Hypertonic.
Yes, indeed. And I'm going to make my cell sad. It's dead. And that's because hypertonic solutions cause a phenomenon called crenation, which is just a fancy science word for wrinkling. But in living cells, that pretty much means death. Like you can't really survive that. This is one of the reasons why being dehydrated is so bad for you. So the implication here, because this process is happening due to osmosis, and we know osmosis is passive, is that if water is just moving out of this cell in droves, it must mean that the concentration of solutes, again, we don't know or care which one, in the beaker is greater than in the cell. So that is correct. This one is hypertonic. So you probably noticed in your little virtual osmosis experiment that some of your bags, which you're using to simulate cells in that exercise, you probably noticed that some of your bags lost weight. So what that means is water moved out of them. So you can surmise or hypothesize based on that observation that the solution in that beaker was hypertonic relative to our little imagined cell. And hyper means more than. So in this case, the solution surrounding the cell had more solutes than the cell did. And finally, we have water entering the cell. And again, this is due to osmosis, and we know that's passive. And water likes to move towards solutes, or another way to say that is water likes to move from an area where there's a lot of water to an area where there's not very much water. So if I see a bunch of water entering the cell, and in this case, so much water is entering the cell that the membrane itself is bursting. So it's like overfilling a water balloon. That means that forgot to write the R, E in beaker. The amount of solutes in the beaker is less than the amount of solutes in the cell. So it's the opposite case of beaker B. We've got a cell with an internal environment that's got lots of solutes and a solution that doesn't have as many as the inside of the cell. So water is going to move into the cell. And in this case, the difference is steep enough that the cell has taken on so much water that it pops, basically. That's not always the case, but I'm using it to make a point here. So in this case, we would say that beaker C is hypotonic. Again, relative to the cell. So you'll notice that I'm talking about tonicity specifically as it relates to a cell interacting with its surroundings. That's really important. If I handed you a glass of water and I told you this solution is hypertonic, and you looked at the water and you didn't see anything in there, a good question, an appropriate question for you to ask me would be, hypertonic to what exactly? That's because hypertonic, hypotonic, and isotonic, they're all relative terms, meaning that they're terms where you're comparing two things. And so the words don't mean much all by themselves. It's not like, because like, I'll give you an example of what I mean. How about that? Okay, so we've established our tonicity rules in solution. So now I'm going to put two cells in the same beaker. We're going to watch the behavior of those two cells, and we're going to describe the solution using tonicity again. So this is where it gets a little bit trickier. So what I've just drawn you is the basics. And now I need to get an eraser and make my eraser big. Sorry, I could just trash the entire page, but that would get rid of my definitions, and I don't want to do that. So this is going to take just a second. Imagine there's elevator music playing while I do this. I know it's boring. Okay, good enough. I don't really care about these dots. Alrighty, so let's draw me a big beaker. I'm gonna make it short and wide. And I'm going to make the solution be green, because I can. And, oh, there we go. So I have this green solution, and let's say same thing as last time. I don't know anything about this solution, so I'm going to try to learn about the solution by putting some cells in it and seeing what happens. But in this case, last time I was dealing with unknown solutions and the solutions were different from each other. Now I just have one solution, so that's the solution. There's no difference. You can't, separate it out. I'm going to put two cells in there. So let's say one of my cells, one must change the size of the dots for this to work. All right. So this is where we get into the relative terms of tonicity. I have two cells in here. One of them has shriveled up, the other one is happy. But it's the same solution. So what that has to mean is that the internal solute concentrations of my cells are different. So without even knowing what specifically the concentrations are, so now we have cell A and cell B, we can take this observation and we can talk about the solution in two ways. So I'm gonna write two sentences with blanks and let you think about it, and then we're gonna fill in those blanks. So sentence one is, so don't say anything yet, just think about it for a moment. And I'm specifically engineering this pause in here because although I do have an active Zoom audience, I'm recording this, so I want to give enough time for people watching this on the recording to have a second to think about this before the answer is revealed.
The green solution is hypertonic to B and hypo to A.
You are correct. Not hypo to A though. A is not changing volume, so the green solution is isotonic to cell A. Oh, I heard someone say, oh, is that an O of suddenly I get it? I hope that's what that means. Okay, so.
What would be the answer for number 2? The green solution is isotonic to cell A?
Yes, let me write those words in for you. And I'll do them.
Thank you so much.
Yeah, I'll do them in a different color too. Okay, so let's fill in our sentences. Green solution is hypertonic to cell B. And it is isotonic to cell A.
So it would have been hypertonic if the cell A was actually like bursting.
Hypotonic.
That's what I meant. Yes.
Yeah, so if the cell was bursting because water was moving into it, then we could say for sentence 2, the green solution is hypotonic. But in this case, I arbitrarily decided that it was isotonic. Because in this scenario, I'm God and I get to decide cell fates. But as you can see, I think this pretty accurately illustrates what I mean when I say that tonicity is a relative term, because here we have two cells existing in the same solution. So the solution isn't changing, but what is changing is the solution's relationship to the internal cells. Does that make sense to everybody?
Yes, I actually have a quick question. So does it mean that cell B is hypotonic to green solution? In other words.
We only use the terms with tonicity to describe solutions, not the cells.
Okay, so that is where the confusion is coming from. So only for the solution.
Yes, yeah. So and as you can see, because so using those words to think about cells is tempting, but then you end up confusing yourself because you're having to use reciprocal terminology for the solution versus the cell, which is why we reserve tonicity only for describing solutions.
Thank you so much. That really made a very good point. Why I got always confused.
Okay,
I am always getting confused. I got it. Thanks.
Awesome. That means I'm doing my job correctly, which makes me really happy. So thank you. I'm glad to hear you say that. So although we appear to have resolved that issue, I do still want to talk about one more thing. And that is osmolarity and osmotic pressure, because it's related to tonicity, kind of, but they're not exactly the same thing. So I'm gonna clear my board and we're gonna look at some boxes, and we're going to assume that these boxes contain solution. I'm not going to take the time to draw it, but I am going to draw what's in the boxes. And I'm going to try really hard to make them isovolumetric, which is a word that means the same volume. But I'm only pretty good at drawing squares. I'm not great at it. So just assume these are the same size, okay? Thanks. All right, so I'm gonna write some ions in here and some other stuff. So just bear with me while I do this. Oops, not squares. There we go. Okay, so I have a solution in, let's give it a name, box A, just to be boring. And then we've got box B over here. So now I need to include some things in box B. So we could have done that better. There we go.
Mm-hmm.
Should say urea, not uvea. Okay, so assume boxes A and B contain equal amounts of water with dissolved stuff. So if you just give this a quick glance based on what's in there, you'll notice that although box A and box B have the same amount of water in them, the stuff that's dissolved in that water is not the same, correct?
Mm-hmm.
So here's the deal with that. This is where we have to take membrane permeability into account because of osmosis. So with regard to osmosis, I'm going to write my golden rule for osmosis. So there's the traditional definition of osmosis, which is counterintuitive and tricky to understand. My way of thinking about it, I consider to be easier to understand, and that is just the rule of osmosis is that water goes where solutes are. And note that I don't specify which solutes. You know why? Well, water doesn't care. So although we're looking at box A and box B, and we know that there's different stuff dissolved in them, from a water perspective, these two boxes aren't different. And here's why. From a water perspective, it doesn't care that these are sodiums. So we're just going to black those out. And it doesn't care that these are potassiums. It doesn't care that these are chlorides. It doesn't care that these are glucoses or a magnesium. Water is just like, oh, there's solutes over there. Cool. Don't care which. Same deal over here. And if I go in and I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 solutes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 solutes. So as far as thinking about these solutions as on terms of their ability to attract water via osmosis, these two solutions would be isoosmotic, which I can rephrase as being same ability to osmotically attract water. So water does not care what solutes are dissolved. It just wants to go where they are. So when you use the suffix osmotic instead of tonic, now we're not talking about a solution on terms of how it affects a cell. We're using a slightly different way of speaking. In this case, I'm telling you how likely or unlikely that solution is to attract some water compared with another solution. So isotonic you use to describe solutions and how they tend to affect cells. Osmotic is a way that you can compare two solutions independently of cells, just on terms of comparing their ability to attract water osmotically. So let's finish up by using this in an example. So I'm going to draw actually, hold on, I want to do three boxes. We're going to assume that they all have equal volumes. And I'm trying to draw these lines as in the middle as I can. So assume that they're equal for me. However, I don't like this one, so I'm going to redraw it. That's better. No, it's not. I really suck at making equal sides of things. Okay, that's as good as it's going to get, probably. Alrighty. So since I know that water does not care what solutes there are, I'm just going to pick a color that I like, which is this kind of magenta E1. Okay, so let me label my boxes. So this is 1. And I'm using numbers now because I want to label my sides A and B. So let's consider the terminology around box 1 first. So the solution inside A is blank to side B. Is it hyperosmotic or hypoosmotic?
Hypo.
Not quite, hyper. So remember, dots are solutes, but they also represent a solution's ability to osmotically attract water. So if we assume that this membrane on side A is permeable to water, which means that we can let osmosis happen across it, that means water is going to move from side B towards side A, right?
Right.
Because water wants to be where the solutes are at. So side A is hyperosmotic to side B. And you can just flip that sentence around and say side B is hypoosmotic to side A. So now let's consider box number 2. Do I have to change anything about these 2 sentences to make them still be true about box number 2?
No.
No, right? Because even though side A in box 2 doesn't have as many solutes as side A in box 1, it still has more than side B, so my sentences remain true. Now what we're going to do in box 3 is we're going to combine, and we're going to use this terminology to talk about the 2 sides in box 3. So now we're no longer comparing a solute-rich solution to a solution with no solutes. We're going to compare 2 different solutions, each of them having some solutes. And I just counted. This one has 13 solutes. Again, doesn't matter what. They could be all the same. They could be all different. Water does not care. And then this one has 5. So let's do our sentences again. So again, thinking about these solutions and comparing them only on terms of their ability to attract water, do I have to make any modifications to the first 2 sentences I wrote?
No.
Nope, I don't. It's still true because the left side, side A, still has more solutes.
I have a question.
Yeah.
So even if on box 3,
Mm-hmm.
let's say that side A only had 1 more than B, then it would still stay true, right?
Yes. The only time in which they would be isoosmotic is if they had the same amount of solutes.
What about ratio? Like the same amount of water to solid on both.
So if you had the same amount of water to solutes on both sides, you would still consider them to be isoosmotic. The only reason that I took the volume out of the equation,
Right.
because to simplify it, but the ratio thing does hold. So like, actually, it's a really good point. Let's apply that principle really quick just to illustrate it visually. So draw some new boxes here. Yeah, come on, squares. That's what I want. I want squares. So I'm going to say that this box contains, dang it, I keep doing that, 3 liters of water. And I'm going to put a membrane in my box. And my membrane is about 1/3 of the way across. So on this side, this is 1 liter. And this is 2 liters. So let's add my solutes. So I'm going to say again, I'm not going to say what solutes they are because it doesn't matter. The concentration on the left side is, and we always express this in concentration, right? And concentration is a ratio, it's solutes per volume. So 3 solutes per liter. And on the other side, we have 6 solutes per 2 liters, which you can, of course, simplify
Right.
to 3 solutes per liter. So even though there appears to be some asymmetry here, you are absolutely correct. At the end of the day, it is the ratio that matters. So if I told you that this barrier was only permeable to water, you would expect water to move from the left to the right at the same rate as water moving from the right to the left. So it's not that water's not moving at all, but there would be no net water movement. And the net is really important. So if you were to subtract water moving to the left from water moving to the right, you would get 0. Alrighty, so that sums up discussions of lab 4 and osmosis and tonicity and cell behaviors. And I am now going to end the recording.